All right, so today we're going to tackle one of the biggest, most powerful ideas in all of science. We're talking about Newton's law of universal gravitation. This is the story of how a single, simple thought, maybe from a falling apple, maybe not, completely changed how we see everything. It's about how we connected our own world, right here, to the vastness of the cosmos in a way nobody had ever dreamed of before.
So let's start with the question that really bugged people for centuries. What in the world does a falling apple have to do with the moon orbiting the Earth? I mean, think about it. One falls straight down, thud, hits the ground. The other just seems to float up there, circling us, totally separate. For a long, long time, everyone just assumed they were two completely different things, playing by totally different rules.
And that's because before Newton came along, the scientific world was basically split right down the middle. You had one set of rules for us down here on Earth, and a completely different and supposedly more perfect set of rules for everything up in the heavens.
I mean, it kind of makes sense when you think about it from their perspective. Down here on Earth, physics felt, messy. You've got friction, things falling, stuff rolling to a stop. But up in the heavens, that was the realm of elegance, of perfect circles, of what they thought of as divine clockwork. The two just didn't seem connected at all. There was no single idea that could possibly explain both a falling apple and the orbiting moon.
And then, 1687, Isaac Newton drops his masterpiece, the Principia Mathematica. And just everything changes. He puts forward this incredibly radical idea. What if there's just one law, a single universal law that explains motion, not just on Earth, not just in the heavens, but everywhere? And this is the absolute core of his genius. Newton basically said, you see that force pulling the apple to the ground? It's the exact same force holding the moon in orbit. He realized the moon is, in a way, constantly falling toward the Earth. It's just moving so fast sideways that it keeps missing. And with that one thought, this principle of universality, he stitched the heavens and the Earth together for the very first time.
So Newton boiled this force down to two really simple relationships. The first one is pretty intuitive. The more stuff, the more mass an object has, the stronger its gravitational pull. Right? That's why you feel the pull of the entire planet Earth beneath your feet, but you don't feel any pull from, say, the person sitting next to you. It's simple. More mass equals more pull.
And the second part is just as straightforward. The force gets weaker the farther apart things are. Again, that makes sense. But the real magic is that Newton figured out exactly how much weaker it gets, and that little detail is the key to everything.
And here it is, the whole idea, captured in one beautiful, elegant equation. The force, F, is equal to G. Think of G as a kind of cosmic tuning knob, the universe's own special number for gravity, and we'll talk more about that in a sec, times the two masses, all divided by the distance between them, squared. And with this simple formula, you could suddenly describe the motion of pretty much everything, from a cannonball to a planet. Okay, so that little r squared on the bottom of the equation, that is a huge deal. It's what we call the inverse square law. And what it means is this. If you double the distance between two things, the gravity between them doesn't just get cut in half. No way. It drops to just 1/4 of what it was. It's this really rapid fall-off in strength that makes all the orbits in our solar system so stable and predictable. But there was a catch, a big one. Newton gave us the blueprint. The equation was perfect, but there was one number missing. He had no idea what the value of G, that gravitational constant, was. It's like having a perfect recipe, but not knowing how hot to set the oven. Without G, you couldn't calculate the actual force. The universe had a rulebook, but a key piece of information was missing for more than 100 years. And this timeline really puts that into perspective. We're talking 111 years, where Newton's law was this amazing theoretical framework, but you couldn't use it to get exact answers. Then, in 1798, this brilliant, kind of reclusive scientist named Henry Cavendish decides he's going to be the one to finally pin down that number. And the experiment he designed was just mind-blowingly delicate. He used something called a torsion balance, which is basically a wire that twists, to measure the super tiny gravitational pull between some big lead balls and some small lead balls, right there in his laboratory. And by measuring how much that wire twisted, he could calculate G. And once he had G, humanity could suddenly do something that sounds impossible. We could calculate the mass of our own planet. He literally weighed the world. Okay, so now with the value of G, Newton's law wasn't just a theory anymore. It was a predictive powerhouse. It explained why the ocean tides rise and fall. That's the moon's pull. And get this, When astronomers noticed the planet Uranus was wobbling a bit in its orbit, not quite following the rules, they used Newton's math to say, hey, there must be another planet out there pulling on it. They calculated where it should be, pointed their telescopes there, and boom, they discovered Neptune. It wasn't just describing the universe. It was telling us where to find new parts of it.
So, for the next couple hundred years, Newton's theory was king. It seemed perfect, absolutely untouchable. But you know how science works. Our measurements got better, more and more precise, and eventually, we started to see a few tiny little cracks in this seemingly perfect theory.
Yeah, there were two really stubborn glitches that just wouldn't go away. First, there was Mercury. Its orbit wobbled or precessed just a tiny bit more than Newton's math said it should. It was a small error, but it was always there. The second problem was even weirder. Newton's law implied that gravity acted instantly everywhere. So if the sun just, poof, vanished, Earth would instantly fly off into space. But we knew that light takes 8 minutes to get here from the sun. So how could gravity be faster than light? It didn't make any sense.
Well, those little cracks were just the opening that was needed for the next giant leap in physics. And the person who was going to take that leap would completely redefine gravity itself. You know who I'm talking about, Albert Einstein.
And the genius here is that it's a complete paradigm shift. See, Newton thought of gravity as this invisible rope, this force pulling things together across space. Einstein comes along and says, what if there is no force? What if there's no pull at all? His idea was that heavy objects, like the sun, actually bend and warp the very fabric of space-time around them. And planets aren't being pulled, they're just rolling along the curves.
This really breaks down the key differences, right? Einstein's general relativity says gravity isn't a force, it's just geometry, the shape of space-time. And its influence? It travels at the speed of light, which totally solves that instantaneous action problem. And the real kicker? When you run the numbers with Einstein's equations, they predict Mercury's weird little wobble perfectly. The glitch was gone.
So does this mean Newton was just wrong? Well, no, not at all. This is the beautiful thing about science. Einstein's theory didn't throw Newton's out, it absorbed it. It showed us that Newton's law is an incredibly accurate approximation of reality as long as you're not in a super intense gravitational field. So what's the bottom line here? The truth is, for almost everything we do in our daily lives, and even in space exploration, Newton's law is the one we use. Unless you're dealing with something extreme, like a black hole or the entire history of the cosmos, Newton's math is simpler and it works perfectly. When NASA sends a rover to Mars, guess what equations they're using? Yep, Newton's. It's still the essential go-to tool for getting things done.
And that kind of leaves us with a final thought, doesn't it? The whole story of gravity, from Newton to Einstein, it just goes to show you that even our most fundamental truths about how the universe works can be totally reshaped. What was once a mysterious force pulling us down is now seen as the very curvature of space-time. It really makes you wonder, what other big ideas that we take for granted today are just waiting for the next revolution, the next great leap?